The last speaker for the day is Mitesh Goyal, who is an Associate Technical Director at Samsung Semiconductor India Research and a sponsored PhD candidate at IISc Bangalore, working on low-trigger SCR-based ESD protection. He has 18 years of industry experience at ST, Intel and Samsung, and he is an NIT Trichy graduate with 10 granted patents and several IEEE publications.
Okay, so I'll stick to the place because I think I need to use the laser pointer. Okay, thank you for the kind introduction, and a big thank you to the DESE Management Committee and the organizing committee for this event. So, good evening everyone. I'll largely present on my work on the SCR devices, which especially used for the ESD protection, right? So this I'll present on behalf of a research team which has people from both Samsung and IISc. The main purpose is to present the key idea which is actually used in a normal SCR, which I'll present today, but the same idea can be extended to lot many SCR device types. And what I will cover is the benefits of using the TCAD based mixed mode simulations and how can it help in the design and technology co-optimization, and how we can create a reference methodology to perform this kind of innovations. Finally, what we will do is we'll compare the ESD characteristics of the novel SCR, because we have implemented it in bulk planar technology. The result I'll present here will be 28 nanometer based technology implementation results, and then we have also implemented them in the 8 nanometer FinFET technology, and again we can correlate the same kind of results there. Okay, so first of all, I'll give a brief introduction about the advantages and the limitations of the SCR, and then I'll introduce to you the work which we have done, and finally I'll give a brief introduction about how we make the decisions using the TCAD based simulations, and finally how the experiments correlate to our TCAD based simulations. Okay, so here are the three key trends in the ESD world. So ESD is one of the key IPs used in the industry for the protection of the ICs on the IO ports, right? So ESD, when you talk about ESD is like a personal security guard to your ICs. Now what is happening in, what do you expect from your personal security guard is to not act when everything is normal, right? So this is that limit. So as the technology node is scaling, the voltage, the operation voltage is falling with each technology node. Also, what is also you expect from your security guard is to act before the damage is done, right? So this limit is the damage line, or is the breakdown voltage with each technology node. So now, since the most vulnerable part in the IC is the gate oxide, and as you know, in order to improve the performance of the MOSFET, the gate oxide is becoming more and more thinner. So the breakdown voltage for the MOSFETs are also falling as the technology node is scaling. But nevertheless, what is happening is that the ESD current spec remains the same. The human resistance is not changing, and it still remains as 2/3 of an ampere for all the technology nodes, right? Because the design window available to a designer is shrinking while the spec for ESD protection remain the same. This is one of the key problems in the ESD world today. The second trend I want to highlight here is that the traditional methods of ESD protection, which involves a dual diode along with a power clamp, is no more feasible because of the new packaging techniques. So now the area availability is too low, the area requirement for these diodes is very high, the parasitic capacitance and the leakage which these diodes give out is totally unacceptable for a modern IC. Third, as you see, and this is from the industry council, is as the data rates are increasing, of course, as we are getting newer and newer applications and the devices, what is happening is, of course, the data rate is increasing. Now, in order to support the higher data rates, the parasitic capacitive loading budget is decreasing, right? So, I mean, it is now of the order of just few femtofarads, right? So, few tens of femtofarads. So these are the three trends, and because of this, as I told you, SCR is a device of choice, because in comparison to other traditional ESD protection devices, which largely comprises of gate grounded MOSFETs and the diodes, SCR gives out the lowest parasitic capacitance. Now, what is an SCR? SCR is the thyristor. It's a 4-terminal device. So we have the anode, the cathode. So generally the anode is the emitter of the PNP device, and the cathode is the emitter of the NPN device. The good thing about the SCR it has a very high failure current. It has very low R-on. So once it is on, it works really beautifully. It has low parasitic capacitance per unit area. But the traditional problems with the SCR are, it has a deep snapback. So by the time it turns on, the damage is done. It has a latch-up problem because it has very good coupling of the parasitic transistor, both the NPN and PNP. The holding voltage is pretty low for the SCR. And now for a modern factories where the chips are made, the CDM timelines are more critical. So the slower turn on time of the SCR still remains to be a critical problem. But what we can also do is we can reduce the area required for the secondary protection of the ESD circuit using SCRs, and of course we can continue to use the SCR as the primary protection devices. Okay, so with this brief background, let me also cover what creating a practical SCR-based solution is very difficult, right? So what we need to do is, in order to trigger it earlier than the avalanche breakdown voltage, we need to create a trigger circuit, or we need to do other circuit techniques in order to lower the trigger voltage of an SCR. So one of the popular method is to use a trigger circuit and use a triggering point, and to create a triggering point in the SCR, which is another P plus diffusion region in the P well. And once we inject the current, and what we will see also, that once you inject higher and higher current into the trigger terminal, the trigger voltage of the SCR will fall, right? And more it will come in that ESD design window. Now there are a lot of works related to this but I would like to explain in detail the trigger circuit, which is very popular. This is a very simple trigger circuit which consists of a resistor, capacitor and an inverter circuit. So typically in an ESD time domain, which is generally in the range of picoseconds, so what we do is we turn on this PMOS, we inject the current on the P-trig terminal, and in the normal functional mode, when the chip is operating in the normal region, in the functional mode, we charge this capacitor, we turn on this NMOS, and we connect this P-trig to the ground, right, which is like just acts like another ground terminal. Now what did we do new here, right? So what we did is, after a lot of techniques and evaluations and simulations, we came up with another diffusion region in the N well, and we call this terminal as the NPIC terminal. Now what is the use of this NPIC terminal in the whole scheme of things is, I'll explain in the next two slides. So in the next two slides, I'll explain to you the two local clamp configurations in which the SCR is used. So an SCR, like a local clamp configuration, you connect a device between the two pins. Like you connect a device between the IO and the VSS, and since the ESD protection can occur between any of the pins, you also need to create a local clamp configuration which you can connect between the IO and VDD, the supply pin.